Welcome back to the workshop for our almost last video on properties of trees. It's our last video on the properties, but we also want to take a look at an example in one more video. So in our last video of properties here, we actually want to look at some equivalencies, what it really means for a graph to be a tree. So let's take a look at these equivalencies. All right, so for a tree, T, or a graph, right? A graph T. We say that it is a tree, okay? And each of the following things is equivalent to saying it's a tree or equivalent to one another. So if T is connected and the number of vertices is one more than the number of edges, then we could also say it's a tree. Or if the graph has no cycles and the number of vertices is one more than the number of edges, then we could also say it's a tree. So essentially what we get is if we know it's connected and we know that condition on the number of edges, then we know that it contains no cycles. Excellent. Or if we know that it contains no cycles and satisfies the condition about the number of edges, then yes, we know that it's connected. Okay. So with that, both of those allow us to conclude, yes, it is a tree. All right, we could also give it simply as a tree is any graph where there is exactly one simple path between each pair of vertices in the graph. That's equivalent to being a tree. If there's exactly one simple path, then of course we're not going to end up with any cycles. And since there is a path, right, we have that it's connected. So that makes sense. The graph is connected, and the removal of any edge results in a graph that is not connected. So that's really quite interesting. That's going back to this property here and saying that we only need this thing right here. We only need the idea that if we remove an edge, it's disconnected. Okay, that's sufficient to know that the graph is a tree. Now it can't be just one. So if I were to have something like, let's give an example here. By removing one particular edge and finding that it's disconnected doesn't mean that it's a tree. Of course, this one is not. But if I were to, for example, remove this edge, it would not be disconnected. So being able to remove one doesn't give us that it's a tree. We have to be able to remove any edge and have it be disconnected. All right, so any edge. So if the graph has no cycles and the addition of any the addition of an edge between any non-adjacent vertices results in a graph with a cycle. That's saying here, if it has no cycles to begin with and this additional condition is satisfied, then that is sufficient to know that it's a tree. Okay, so we said that if it's a tree, then we get all of these things, but we actually have the ability to go backwards as well. We have the ability to go backwards from many of these properties to the fact that the graph is in fact a tree. Okay, so we won't spend necessarily a ton of time working all possible ways on these properties because there are a lot of properties and there are a lot of ways that we could go about this that exceed what the scope of the course really is. So we need to be familiar with them and have an understanding of when we have a tree and when we don't have a tree. So we'll take a look at an example in our next video that uses some of these properties. And hopefully in our section or our chapter on writing proofs, we'll be able to return to this and write some proofs about these as well. So they'll reappear a little bit later too. All right, so I'll see you guys back in the workshop for one more video on properties of trees.